Hey everyone, welcome back. Today we're going to wrap up our discussion over fixed axis rotation. And so far we've compared our position with respect to time to our rotational velocity acceleration. We came up with this relationship between mass and rotational mass, moment of inertia. And then we compared Newton's second law, F equals ma, to the Newton's second law rotational law, which is our torque equals I alpha. And so these last two things we need to talk about are momentum and kinetic energy. So if you think back when we talked about momentum, we looked at the mass of an object and its velocity, and the translational momentum was defined as P equals mv, mass times velocity, and our kinetic energy was equal to 1/2 mv squared. The problem is when we talk about rotation is we're constantly changing direction. So if we try to represent this same mass here and here with this mass times velocity, the problem would be is that our velocity vector would constantly be changing because we're constantly changing direction. So if we use an angular momentum instead to discuss this, we'll have one vector that's normal to this plane, that's a plane of rotation, and we won't need to worry about exactly where in this rotation this object is to describe its momentum. So angular momentum's defined by the cross product of r and p, but this is only for a point mass. So if we continue and make some substitutions, we should be able to come up with a general equation of how to represent angular momentum using this as an example. So momentum, if we replace it with mass times velocity, our angular momentum is going to become the r crossed with mass times velocity, where velocity is equal to our radius times omega, our radius times our angular velocity. So if we plug that into this equation up here, we end up with our angular momentum equals our mass. I pulled that out in front because it's not going to affect our cross product. It's a scalar quantity. It's going to be our mass times our radius crossed with another radius multiplied by our angular velocity. And when you take the cross product of the r crossed with r, we end up getting the magnitude squared of r. So we could replace that, and we end up with this L equals mr squared omega. So that doesn't really look familiar, but if we look back at our moment of inertia table, when we have a spinning point mass, if you think about if it was spinning really fast, it would appear to be a hoop or a thin wall hollow cylinder. So the moment of inertia for a point mass rotating is equal to mr squared, which is exactly what we see here. We have the moment of inertia of a hoop. So if we just make the general claim that our angular momentum is going to be equal to I omega. And so we could do the same thing with kinetic energy. We have kinetic energy translational is equal to 1/2 mv squared. Our velocity squared is equal to r omega squared. Same relationship we used before, we're just squaring it. We could substitute that in for our velocity squared, and we see the same term, our mr squared, or the I of a hoop. And we could once again make the claim that we could replace this middle term, our I hoop, with any moment of inertia and find that our kinetic energy is going to be equal to 1/2 I omega squared, which shouldn't be too hard to remember because it's just our 1/2 angular mass times our angular velocity squared, where our translational kinetic energy, let's go back to our table. You can see that at the bottom two comparisons that our momentum is just our mass times velocity for translational, and our rotational, it's just our angular mass times our angular velocity. And kinetic energy for translational is 1/2 mv squared, and is now going to be 1/2 our angular mass, moment of inertia, I, times our angular velocity squared. So they're pretty similar. So let's take a look at this example. There's a lot going on here, but let's just walk through it. So first off, we got this disc that this person's standing on. And this disc is supposed to be a merry-go-round, and it has a radius of 2 meters, and it's spinning at 5 radians a second. And the mass of this merry-go-round is 400 kilograms. And it has some person standing on it initially 1.5 meters from its axis of rotation, and that person weighs 120 kilograms. And so what's going to happen here is this person's friend is going to come and jump on the merry-go-round while it's spinning. This person isn't moving. They're only moving anti-parallel to the radius of this spinning disc. So them jumping on isn't going to affect the motion, the circular motion of the whole system in terms of momentum, because they're only going to be, when they land on here, they're only going to be applying a force, like I said, anti-parallel to the radius, which in our previous video we saw that isn't going to apply a torque to the system. It only will, it would only affect the energy of the system if the person was jumping and landing somewhat with some component that is perpendicular to the radius. So we don't need to worry about that here. So only thing that this person's changing is the moment of inertia of this whole system. So what we're being asked is, if this person lands on the merry-go-round as it's spinning at 5 radians per second, what will this person one's final velocity be standing, his or her tangential velocity standing on this disc? Well, first, it will be easier to find our angular velocity final before trying to find our tangential velocity of this person. And so that's where our conservation of angular momentum comes into play. It becomes helpful, just like when we had our problems with crashing cars and whatever else we talked about. We could just set up our momentum initial and our momentum final and solve for whatever we're looking for. So if we do that, we see that our initial angular momentum is going to be our sum of our moment of inertias. We initially only have I1, which is the moment of inertia of the person standing on the merry-go-round, and I3, which is the moment of inertia of the merry-go-round. And then after person 2 lands on the merry-go-round, we're going to have to consider all three moments of inertia multiplied by our final angular velocity. So, as I mentioned before, the person standing on the merry-go-round, as they spin, they create a hoop. And looking at our table, moment of inertia table, letter G gives us the moment of inertia for person 1. So we could substitute I1 with M1R1 squared, and then the moment of inertia for our disk is going to be represented by a solid cylinder, which is equal to 1/2 mr squared. So we'll substitute I3 for that. We got 1/2 m3r squared, and then it's multiplied by our initial angular velocity. And then our final angular momentum, we have this new person jumping on the merry-go-round, so we have to just sum their angular momentum with, or their moment of inertia with the moment of inertia in person 1 and the moment of inertia of the merry-go-round, and that will be multiplied by our final angular velocity. So we do the algebra, we just divide over the coefficient on the right side of the equation, we end up with this. And since we're not actually interested in solving for the final angular velocity, what we're interested in is finding the velocity, the tangential velocity of person 1. how they're moving. If let's say if they slid off this merry-go-round, how fast they would be going, their tangential velocity. So as we've seen before, our tangential velocity is just the radius of the whatever point we're interested in. So radius 1 is where the person's standing, and that's multiplied by our final angular velocity. So solving for final angular velocity, we just get v1 over r1, and then we could substitute that into our previous equation, and we see that our velocity 1 over r1 is the same as what we had before. We're just going to multiply over by r1, which I don't have written here. Which now gives us our velocity of person 1, our tangential velocity of person 1 in terms of all constants. We're given all of these. We know what the mass of person 1 is. We know the mass of the merry-go-round, person 2, and the radius of all of them. So we could plug in all of our values, and we end up with this mess, which comes out to be 7.25 meters per second. So once again, this answer is telling us how fast this person is going tangential to our rotation. And so let's see this in action. So this is a little different idea, but it's the same idea, kind of, where we're dealing with changing the moment of inertia of an object. In this case, we're not changing the mass or adding an object to it. This guy is pulling a string, and it's collapsing this sphere as it spins, as it rotates. And so as the mass gets closer to its axis of rotation, its moment of inertia is being reduced. But since we have conservation of angular momentum, if our moment of inertia is decreasing, that means that our angular velocity has to increase to conserve our angular momentum. So as you see, as this sphere collapses, as he pulls on the string, our angular velocity starts to increase dramatically. So in the last example, we considered the change in moment of inertia in a system, how that affects our final angular velocity. But what if we, instead of adding a moment of inertia, some other mass, or changing the size of it like we saw in the video, what if we instead rotated our angular velocity so it was pointing in another direction? Looking at this video, we see that this girl is rotating back and forth as she turns this spinning wheel to her one side and the other. And so what's going on is, initially when the clip first starts, right here are basically, if we call into the screen the negative y direction, all of our angular momentum is facing in that direction. Well, if we think back, we know that an object isn't going to change its motion unless there's some force acted on that. So as this girl's tilting the wheel, she's putting a force into the handles of this wheel, and it starts to get her to spin. But why is it that she's spinning to the right and to the left? And why is it that we're and how does this apply to conservation of angular momentum? So I attempted to draw this as simple as possible. So this red cylinder is supposed to represent the girl, and this black wheel inside is the spinning tire that she's holding on to. So if we look at the initial condition, we have this wheel rotating in the ZX plane, and since it's rotating forward, if we follow the right hand rule, our thumb points in the negative y direction. So our angular momentum is going to be I sub w, which is just the moment of inertia of the wheel, multiplied by how fast the wheel's spinning, our angular velocity. But what we do know is that our angular momentum is in the negative y hat direction. So why is it that as she starts to turn the wheel, she starts to spin? So she's going from a vertical wheel spinning forward in the ZY plane, and she's tilting it on the side initially so that the wheel is going to be in the XZ plane. And as we do this, we see that our wheel will now be spinning in, from a top view, a counterclockwise direction, which gives us a positive Z direction. And so because of the conservation of momentum, we didn't have any momentum in the Z direction initially. So as this wheel gains a positive, sorry, I just realized my signs were backwards. So anyways, as it turns into the XY plane, the wheel, it's going to start having a component of of angular momentum in the positive Z direction because it's spinning counterclockwise. So right hand rule, our thumb's pointing in the positive Z direction. But because of conservation of momentum, our girl needs to counter that because in the Z direction, we don't want to have any net angular momentum. So depending on the moment of inertia of the girl and the speed she's spinning, these two should cancel out, causing our angular momentum to equal 0. Well, that shouldn't make sense though, right? Because our initial momentum has some negative y component, but looking at this, our z components cancel, but we don't even have a y component. And so this is one of those problems like when we talked about the change of momentum when we're throwing a ball against a wall. We need to consider everything that's going on here. And what actually happens, if you look, when she first turns the wheel right here to the right, you actually see her head pull forward a little bit right there. And then when she goes back the other direction here to turn back, you could see that her head kind of pulls back ever so slightly. And so what's happening in the X direction is that we're applying a force that we can't really see here because she only has the axis of rotation of the disc that she's standing on in the Z direction. And so that pull forward and back is actually putting that momentum that we should see in the Y direction, what we're calling the negative Y direction, it's putting it into the whole system that's incorporated here, which of course would be the Earth, is the force that the disc she's standing on is pushing on the Earth, so we can't really see that in this example. So once again, with momentum and translational and rotational momentum, we need to be careful of what we're looking at as we talk about it. Because here, as I showed here, just kind of going through this in what I would consider a somewhat logical way, we could explain away why the person starts spinning on that disc as they turn the wheel, but we still end up with 0 angular momentum. Anyways, so this is actually how they is used to steer spaceships, and gyroscopes are also used in ships and whatnot to keep a steady motion and whatnot. So there's a lot of practical applications for spinning objects. All right, so now let's take a look at a kinetic or an energy problem, rotational energy problem. So let's say we have this board. It's this black board. You can think of it like a sheet of wood. It weighs 30 kilograms, and it has one length of 3 meters and the other length 1. And we have an initial angular velocity of 1.2 radians per second and a final angular velocity of 2.4 radians per second. So this thing's angular velocity is doubling over some period. And what we want to know is how much work is done on the board. Well, with translational kinetic energy, we saw that the work done on an object, as long as we're not losing any energy, this board's not rubbing up against anything, so we're not causing heat from friction. We're ignoring air resistance, so we don't have any loss of energy. So we could say that our work done on the board is going to be equal to the change in kinetic energy, which of course is just the kinetic energy final minus the kinetic energy initial. the kinetic energy, as we saw in our first slide, that is equal to 1/2 I omega squared. So for the final, we'll just put a final, initial. And we could simplify this somewhat by pulling out the moment of inertia in front and the 1/2. The moment of inertia of this board isn't changing throughout the process. All it's doing is speeding up. We're not changing its mass or where the axis of rotation is. And so if we go to our moment of inertia table, we have for letter C, our moment of inertia with an axis in the center of a plane with length sides A and B is equal to 1/12 the mass of that object times A squared plus B squared. So that's all this is the moment of inertia of a board, 1/12 mass times A squared plus B squared. And then, of course, we know all of these values. We're given what the lengths of the sides of the boards are. A is 1 meter, B is 3. We're told the mass of the board, and we know what our final and initial angular velocity is. And this 1/24 is just from me pulling this 12 out. So if we plug all that in, we end up with work equals 54 joules. And then there's one more concept that I wanted to talk about today. It's going back to the moment of inertia. We kind of skipped over it, but you guys have at least one homework problem I know of that this will apply. So I told you wouldn't need to calculate moment of inertia as in integrating, but sometimes our objects that are on our table for moment of inertia don't have the axis of rotation exactly where we want. So looking at the moment of inertia table, once again, letter F, the cylinder is what we're going to assume this thing's shaped like that we're working with. We're given the moment of inertia 1/2 mr squared. But as you can see, that axis of rotation's through the center, which I have represented as letter A. This is our rotation. So if this disk was spinning, our moment of inertia for this object at point A is just going to be that 1/2 mr squared. But what if we moved our axis, how this thing's rotating, and let's say instead of being at the center of mass A, we moved it out to point B? Well, looking at our table, we're not going to find much help here. The axis of rotation of all these is either through the center or off to one side, and in our example, we're somewhere in between. So of course we could go back to the definition of moment of inertia and calculate this, which would be a big pain since we would have to come up with some sort of representation of this shape. And at point B isn't so easy. A obviously is simple since it's a circle, but there's something known as the parallel axis theorem. We could figure out if we're asked to find the moment of inertia if the axis is moved from point A to point B. So this is kind of a little cheat. It's helpful at times. I'm not going to prove it here today. You could actually go through if you're interested, and I think the best to kind of demonstrate this to yourself would be take the moment of inertia of A and then take the moment of inertia B, but act as if that rod is twice the has two rods instead of one, pointing to basically make the same shape as A, if that makes sense. Anyways, so the parallel axis theorem tells us, well, one is represented by this, but it tells us that the moment of inertia at some point in an object is equal to the moment of inertia at center of mass, so that was that 1/2 mr squared that we saw from our table, plus the mass of the object times the distance squared. And this distance squared is this distance that we traveled here from A to B, which in this case is just 1.2 meters. And then, of course, we know I center of mass. So I center of mass is represented there. and our d is 1.2. So now we could plug these two knowns into our parallel axis theorem, and we're interested in the moment of inertia at point B. So our I center of mass, 1/2 mr squared, plus mass times distance squared becomes, simplifying this a little bit, just by pulling out the mass, becomes this. And then, of course, we could plug all these values in because we know what they are. So we see here that our moment of inertia at point B is 10.3 kilograms meter squared. And so that's from here to here. So that doesn't really give us much insight unless we really compare it to something. So if we compare it to the moment of inertia at point A, which is our 1/2 mass r squared, and we take the difference between the two, we could see that we had a change in a moment of inertia of 5.8. So as we move away from our center of mass, our rotation of the center of mass, our angular or our moment of inertia is going to increase. And if you've ever grabbed something and spun it that was symmetrical, it's not too difficult to spin it when you're holding it in the center spinning it. But if you grab one end or the other, it is more difficult to rotate that object. And that's because as you move that axis out away from the center of mass, you're increasing the moment of inertia. So I think that's it for today. If you guys have any questions, email me. I'm going to do one more video over all this rotational stuff, just covering some random questions. I'm sure there's a few little things that we've skipped over. But if you have any questions, email me. Like I said, I'm going to be doing a video at least once a week of just random problems to help you guys out if you need it from the homework. And also keep your eyes open. I'm going to send you we need to keep up with our participation points, and I kind of want to see where everyone's at. I'm not really sure if everyone's been following the videos or whatnot, so I just want to make sure that everyone's on track. Anyways, I hope you guys have a good weekend. I'll talk to you next week.